Hi, everyone. My name is Clay Stevens, and I'm a PhD student at the University of Nebraska-Lincoln. I would like to talk to you today about some research that my colleagues and I have done into ways that we can explore the efficiency of self-organizing software development teams with some ideas that are potentially new to the software engineering community, in which we drew from game theory research. We're very excited about it, and we think that it's a great new avenue for software engineers to look into the behavior of developers in their community. Uh, to, to start, we should harken back about 20 years to the old days of software development, which was mostly a sort of centralized top-down project management situation where a manager or team lead might have a giant Gantt chart including all of the different tasks that needed done, and they would assign them out to the developers as they saw fit. For the last couple of decades, there's been a push away from that sort of centralized top-down approach to becoming more agile and using a technique like Scrum or any other agile technique to develop software. And one of the tenets of the Agile Manifesto of 2001 is that agile teams are self-organizing, in that the developers themselves get to pick what tasks they are assigned and which ones they're working on at any given time. This supposedly comes with a variety of benefits: increased developer satisfaction, increased productivity, the ability to meet changing requirements more effectively, but there may also be some downsides. For instance, if all of the developers start to be thinking about their own selfish desires instead of those of the team, what is that going to do to team productivity? It may be that the team may perform less well and things may start to go south if everyone is looking out for number one and not looking out for the goals of the whole group. So our proposal is that we can actually study this behavior. We can shine a light onto the dark spots of agile self-organizing teams by looking at it as a strategic behavior. In this case, a strategic behavior is one where each developer is optimizing for their own best outcome, while also considering all of the choices that are made by the other developers of the team. Since they're not working in a vacuum, if they want to more practically optimize for themselves, they're going to have to consider what everyone else is doing as well. This can be studied by modeling it as a game, as defined by game theory research, which includes a set of players, in this case the developers, who are working on multiple tasks, each of whom is trying to maximize a particular utility or payoff function. They do this by selecting a particular strategy. For us, that is the allocation of work units, be it hours or story points to the individual tasks. And the goal is to find a Nash equilibrium, a place where none of the players has any benefit from doing something different with everyone else staying the same. In other words, we want to find a set of strategies where each player assigns a set of tasks or set of work hours to a set of tasks, such that none of the players is better off by reassigning their tasks with everyone else staying the same. Now, in many types of games, this one included, there are multiple Nash equilibria, lots of different strategies that no one would really be better off by individually changing. In that case, in order to compare them, we have to consider something else. We have to consider some other metric based on the global set of strategies, which in this case are referred to as social goods. So we want to maximize some social good. There are lots of different social goods available. In our particular case for self-organizing teams, we looked at two. We looked at the overall social welfare, which is the sum of all of the payoff functions for all of the players for a given set of strategies, which we used as a metric for their happiness or satisfaction. And we also looked at a measure of the productivity of the team, which we counted by assigning each of the tasks a particular threshold of work hours that needed to be allocated to the task in order to complete it. We then summed up all of the thresholds for the completed tasks, that is, tasks where the developer's allocation met the threshold, and we use that as a proxy for the productivity of the team as a whole, in each Nash equilibrium, and in fact in each allocation of strategies altogether. By using things like the social welfare or the threshold or other social good metrics in terms of Nash equilibria, we can potentially find out some things about how self-organizing teams work. As an example, we tested with a simulation a hypothesis that smaller development teams self-organize more efficiently than larger ones. There's some colloquial support for this. In particular, we looked at the sort of two pizza rule, famously attributed to Jeff Bezos, that says that no team should be so large that 2 pizzas can't feed everyone. There's also some historical support for this in the Mythical Man Month, the book by Fred Brooks, where he famously says that adding developers to a late project will in fact make it later. All of these sort of provide some evidence that smaller teams are better and more efficient than larger ones. We can measure this efficiency by using 2 metrics we also drew from game theory research. The price of stability, which compares the best possible value of the social goods in any assignment of strategies, to the best of the Nash equilibrium, the best set of strategies where no one would want to deviate. That provides sort of a upper bound for the inefficiency of self-organizing teams. We also have the price of anarchy, which is comparing the optimum to the worst Nash equilibrium, to the time when all the developers are okay with it, but it turns out to be the worst for the company. In either case, a higher price means that self-organization is less efficient. So we simulated this by running a bunch of randomized values for our model's metrics, and tried to gather some information about what happens to our social goods in a case where the developers are self-organizing. We computed what the Nash equilibria are and measured the social goods at each of those points, as well as finding the global optimum of all of the possible assignments to compare against for the price of anarchy and the price of stability. First, for social welfare, indicated by the SW on these graphs, we saw that the median price of stability and price of anarchy both increased as the number of developers on the team increased. This provides some initial evidence that smaller self-organizing teams do seem to be more efficient than larger ones, based on the increase of the POA and POS as team size increases. For our other social good, the threshold completed, things were a little bit less clear. In this case, we varied the number of tasks and the number of developers, and looked at the Nash equilibria versus the global optimum. In this case, we had lots of situations where the self-organizing teams, the Nash equilibrium states, did not complete any thresholds at all. No projects were completed. Those are represented by these yellow inf boxes on each of these graphs. So that provides a bit muddier of a picture. In this case, we see that smaller tasks might have, smaller teams with a smaller number of tasks may have more trouble finding an appropriate allocation of work units when they're self-organizing. So it shows that very small self-organizing teams may be unable to finish any tasks at all compared to a centralized top-down team that would be able to complete these tasks. So that doesn't support our hypothesis and suggests that in fact, the smaller teams may not be as good in this case. Now, granted, we only did a very small simulation here, very initial results, and only looked at a couple of the possible social goods. And there are many, many opportunities for future research here. For one thing, our model has lots of different parameters to describe and capture real developer behavior, the kinds of payoffs that they might expect. We might include developer skill or language preferences, the overhead and communication. We may use different social goods, like the increase in skill for learning a new language or something like this. Lots of different variants in the kinds of games we use to model it. We only modeled a single game with complete information, but sprint planning happens every 2 weeks. So that might be an opportunity for future research or extensions of our model as well. And lastly, we also would love to do some human studies here and compare our game theoretic model against real behavior by real developers. In conclusion, however, we introduced to the software engineering community some game theoretic concepts for a model of self-organizing teams. We introduced the price of anarchy and the price of stability to the community and showed some exciting results. So special thanks to the National Science Foundation and the Nebraska Research Initiative for supporting this research. And thanks to you as well for coming to my talk.
Hi there. We're here with Clay Stevens, who's one of the authors of the paper of the video you just watched. And we have a chance to ask Clay some questions. He's in Omaha, Nebraska at the moment.
Hi,
we have
everyone.
a question in the chat. Can you please elaborate a bit on your research design?
All right, sure. So for this particular paper, which I'm sure you've seen, is pretty general and sort of forward-looking. We took our model of a game-theoretic approach to these self-organizing teams, and we essentially randomly generated a bunch of values for things like the utility functions for each of the players, the costs for each of the players for each of the projects, the thresholds for each of the projects, and randomly generated a few, I think 1,000 of these possible allocations of different parameters. And then we ran through them and computed the Nash equilibria for each one, and then computed the price of stability and the price of anarchy, comparing the best score that we received for each of our social goods to the best or the worst of the Nash equilibria. So this right here is really just a random simulation that we've done. We didn't perform any sort of human research. We didn't associate it with any actual projects. This was mostly just to see sort of what we could learn from the kinds of metrics that we're dealing with and how we would go about learning that. But going forward, looking into the future, we would love to have more research that's done specifically to find out whether or not this model actually tracks with reality. So our simulation provides a little bit of support for that, but we definitely have a long way to go still in attaching it to real developer behavior.
And can you say something about sort of the bounds that you put on the values that you had to generate or to simulate, right? Because for tasks, you must have had some bound on task size and some min and max on maybe happiness or other parameters you had. Could you say something about that?
Sure. So for the most part, we actually normally distributed these things. And so I don't remember exactly what we used for our means and for our standard deviations. But in general, we tried to keep them in line with some estimates that we'd received from previous research. We also, in those simulations, I think we used, we represented the skill of the various developers. And for that one, we allowed essentially a 10-fold range. So the lowest developers would say be at a 1 and the highest developers would be at a 10, normally distributed so the mean would fall somewhere in the middle of that. So we kept it to relatively small ranges, usually for some of the values, I think we used between 0 and 1, just to sort of get a proportion for these sorts of things. But realistically, we could do whatever sort of specific values were necessary, I think. I don't know that it would change how the actual model works in this particular general case. The important thing is that we're using the threshold here to determine whether the projects are successful or whether they fail. And we're hoping to track this, hoping to introduce to the software engineering community these ideas of the price of stability and the price of anarchy to sort of bound this analysis.
And we've got just about a minute left, and this is a pretty big question. So do your best in the time remaining. But part of your results showed that smaller teams might not finish tasks, might not finish any tasks. I think the matrices you were showing. So can you say something about how that compares to reality? Because clearly teams do finish tasks even if they're small.
Well, I think what happens there is that hopefully the managers and things that are assigning the size of the tasks would recognize that the tasks are too big. I think our random assignment of tasks did not take that into account, where we had situations where a single developer had a certain amount of hours that they could provide, and they were given 3 projects, each of which were too big. So there's nothing that they could have done there. So that would really be contingent upon, that would be a way where the reality may not match with our simulated model. But even so, that does provide some indication that you have to watch out on your team threshold, your project thresholds, your project sizes, which I think is something that is well known in Scrum planning, is you have to make your tasks relatively small.
So in a way, your simulation had to do a better job of simulating the manager too, to make sure that tasks.
I think so, yeah.
There's a question in the chat we're not going to quite get to, but I'll ask Clay if he can respond to